which is another version of Cosmic Queries. We're just calling it office hours because you can come in with any question at all on any subject. And I got my man Chuck Nice here.
Hey, Neil, what's happening? Of course, brother.
Okay.
How are you, man?
Thanks for doing this.
Hey, it's always my pleasure.
I haven't seen the questions yet.
No, you never do.
One day you'll show me the questions.
No, I will not.
I'll mug you in the street.
Yeah.
Get the question. So what do you have?
That'd be pretty funny, actually. I think I just saw Neil deGrasse Tyson beat the hell out of a guy and run off with some papers. I wonder what was that? What was that about? Yes, of course, we get we take questions from all over the internet, wherever you can find us. And so we always start with a Patreon patron question.
All right, let's do it.
And this is Ari Modi, or Ari Maudi from Patreon. Ari says, hey, I'm from Los Angeles. Some astrophysicists say there will eventually be universe death when the last atoms are ripped apart by the expansion and we enter the big freeze. But we are also told a universe can come from nothing, and taking any volume of empty space and waiting a gazillion years, matter can and does arise from that void. Aren't these contradictions? Why wouldn't something from nothing happen after heat death, if that is a fundamental part of how the universe works? So Ari Maudi,
he totally into that question. He got
everything,
all in,
man,
all up in
it.
In the question.
He was like, I'm going shopping for astrophysics, and I'm going to put everything in the cart.
Everything in. So right now, the temperature of the universe, if you put a thermometer out there,
right,
and it sort of could receive the sort of the energy of the void.
Okay.
It's basically the cosmic microwave background.
Right.
That energy gives you about 3 degrees. But we used to be much hotter when the universe was smaller.
Right.
Okay?
Right.
We've been expanding and cooling. Not fundamentally different in principle. I mean, the mechanisms are the same, but have you ever let air out of a bicycle tire? Does anyone still ride a bicycle?
Of course, yes.
Okay.
I do it all the time, and it's not even my bike. I just walk around Manhattan, I see a bicycle tire, and I'm just like, you know what?
Expanding air is cooler than the air that it was before it expanded.
Okay.
So the air going past your thumb feels cool. It's not just because it's moving, it's actually dropping in temperature by expanding. And so the universe expands and cools. It's a thermodynamic fact.
Okay.
And by the way, we can look to faraway galaxies,
right,
whose light came to us from a time in our past,
right,
and there are measurements you can make and show that galaxy was feeling a warmer temperature in its time than the temperature that we measure today.
That's pretty wild.
It is completely wild.
Because you're not talking about a very a big source. Like that light source is...
It's a light source, yeah, but it's ubiquitous. But it's ubiquitous. So everybody feels it.
Right.
And there's certain...
so now how exactly...
There's certain atoms where the electron will move in a certain way depending on what bath it's in.
There you go.
The bath of light.
I got you.
Yeah. And
that makes sense
they're
now.
a little more excited farther away than they are here.
That makes perfect sense.
So we're not just making this up.
Right.
Okay?
All right.
So...
I hadn't listened. I had to make sure. You know what I mean?
So, as we get twice as big, they drop the temperature in half. 3 times big, it drops it to a third.
So there is a direct inverse proportional relationship to that
inverse
drop?
Proportion. Very good.
Oh, yeah, you like
very
that?
good. I like that.
I did
that was good. I saw what you did there.
With that.
Not just proportional, inverse proportional.
Yeah, exactly.
So as this continues, the temperature of the universe drops. All stars will ultimately burn out as they shut off one by one in the night sky.
Look at that.
As they shut off in the night sky, you can ask, well, are we making new stars? Well, we are with the gas clouds that are still out there.
Right.
But then they make a star, and then that star dies. So the gas gets sort of trapped up in stars that die.
Mm-hmm.
All right. So then there's no more gas to make stars. Then the atoms themselves decay. And ultimately, in about 10 to the 30 years or so, which is a huge number.
Right.
Huge number. The protons decay. the very structure of matter itself loses all integrity.
Wow.
And so the universe ultimately dies not with a bang, but with a whimper.
Right.
And not in fire, but in ice.
It peters out. That's wow.
After I said those poetic words, you say it peters out. Yeah. Is that the best you got for me?
That was the joke. Okay. That was the whole joke.
So this idea that you can get something from nothing, I just want to spend a minute on that, if I can.
Okay.
So if you start with nothing and then create something that has both positive and negative energy in it, all that matters is that the sum, you add them together and you get zero.
Zero. That's it.
Okay? So you can start with nothing, yet have something if the total energy goes to zero.
Right.
So another way to think about that is, let's say you have a level field. And say, I want to dig a hole.
Okay.
So I'm going to dig a hole and stack the dirt over on the left.
Right.
So I keep doing this. I can make a mountain as high as I want.
Right. But you're going to have a hole.
I'm going to have a hole.
Right, exactly.
I'm going to have a hole.
I got a hole. Right.
I got a hole.
There you go.
So, what we're not sure about is whether you create another universe within this universe that has expanded.
Right.
Out of that void. Our best understanding of this multiverse hypothesis is that the universe that's created is not causally connected to what's outside of it. So you could, in principle, have multiple universes popping up into existence.
Right.
But in the expansion and the edge of what that universe is, you have no way to interact with it. So there you have it.
Wow.
We're stuck in this one.
We're stuck in this one, and that's all there is to it.
Yeah.
That's pretty wild.
Yeah.
Man, listen.
He got his money's worth on that one.
You got your money's worth, bro.
That's right.
Yo, Ari, that's a great question. Took us to the
edge of the universe.
To the edge of the universe and back.
Not only in space, but in time.
Could you go to the edge of the universe without space and time?
Actually, once Einstein put forth relativity,
right,
where the fourth dimension is time, and people say, well, that's weird. Why is that? No one has ever been at a place unless it was at a time. No one has ever acknowledged a time unless they were at a place. Think about it. If I say to you, Chuck, I'll meet you tomorrow at 10 o'clock. What's your next question to me?
What are we doing?
No, that's not. Okay, what's your question after that?
Of course, where?
I give you a time, you ask where.
Right.
Okay, I say, Chuck, I'll meet you tomorrow at the corner of 33rd and 3rd. When? We know intuitively that our path through life involves the juxtaposition of space and time. We know that intuitively.
Wow.
We just don't think of it in those terms.
Right.
Because they're measured by such different tools.
Exactly.
A watch and a map.
Right.
Right? So, but in fact, they're conjoined. And Einstein formalized that statement in his theories of relativity.
Amazing. That is great stuff.
You got it.
All right. Let's move on to another question. Hey, how about Woody? It's clearly this is a Disney Pixar character who's just writing in. And Woody would like to know.
Woody.
Do lasers and solar panels work together? We could design and build the components for specific purposes of wireless energy transfer at great distances, which frequency on the light spectrum would be best suited for this task. Then how would you resolve the problem of a 5-watt laser being a dribble like Chuck at 3 a.m. after too many 500 kilowatt laser? What? What the hell is this guy talking about?
Okay, I think I got his point. So what he wants to do is, I have energy here, and I want to put it over there.
Right.
All right? So, by the way, that, when you think about it, is kind of like what war is.
Okay.
What is a battle?
A battle
I have energy here, and I want to put it over there.
Right.
That is kind of what the waging of war is all about.
Mm-hmm.
Right? I have a bow and arrow. I put energy in the arrow here, and then the arrow goes over there. There's a bullet, has energy. There's a bomb. There's a delivery mechanism. Thanks for the sound effects there, Chuck.
Yeah, no worries.
So So I think what he wants to, is it he? Yeah,
Yeah,
Woody, I
yeah,
assume.
yeah.
What he wants to know is, if I have laser energy over here,
Right.
and laser goes fast and it's very directed, can I just have a catcher's mitt somewhere where I want to deliver it,
Right.
and then use it there?
And then use it as energy.
In principle, nothing stopping that.
Right.
Okay? Except the curvature of Earth's surface, if you believe in a round Earth.
Right.
So you can't beam
bend
beam light and bend it.
Right.
Okay? Not on
unless
Earth.
you have a gravitational force that will bend it for you.
Yes, that would work. So on a black hole, you try to send a beam of light, it'll just curve and
Right.
go around the black hole itself. So, but on Earth and sort of normal gravity that we live in, no.
No.
So it has to be a line of sight delivery.
Right.
If it's enough energy to be useful, it's going to be pretty dangerous to cross that beam. I'm just saying.
I shouldn't be laughing.
I know.
It's really serious.
That's
what you're
really
saying.
a serious issue.
But at the same time,
If it's enough energy to do good stuff with it,
right,
it's
enough energy to do some real harm.
You would cut you in half just
Exactly.
walking down the street.
See, what's funny about that
What?
is if you're smart enough to make that happen, but you didn't even think it through.
Completely.
And
yeah.
so you actually do it, and like on the test run, you got the catcher's mitt there,
Mhm.
and you're just like, oh my God, look at this. We've actually figured out a way to transfer energy over great distances, and oh damn, we just killed somebody.
Or a more tragic version of that story was, let's celebrate and dance. And then they accidentally dance
That's
into
in front
the
of
beam,
it.
in front of the beam. And then it kills the inventor
Yeah.
of the...
See, your version has poetic justice.
Right, no, that one. So, yeah, so that's an issue. So so insulated wires. I mean, we were kind of already do that with electricity.
Fiber optics.
Electricity. Well, no, that's information we send by fiber
Right,
optics,
right.
not
Not energy itself. So you're right.
Yes,
Okay.
it's a small amount of energy, but it's not enough
it's not enough to power anything.
to power anything.
Right.
Correct.
I got you.
And what we learned, here's just an interesting. You didn't ask this, but let me put this in the mix.
Okay.
Do you remember everyone's expectation of the future as imagined in the 1950s and 60s? Flying cars,
Right.
motorized walkways. People were thinking that energy would be very accessible. Basically, because it takes energy to fly cars.
Right.
But that's not what became accessible. Information
Right.
became accessible.
It's well, yeah.
So we're living in an information age,
information
and
age.
it costs you nothing energetically to send information.
True.
And as a communicative species, information is it's a highly valued commodity.
Mm-hmm.
So we send information around the world, with no effort. Yes, it's a big effort, but no, the investment of energy that requires is extremely low.
True.
So, so back then, no one imagined a world where. The movie 2001, A Space Odyssey.
Yeah.
The computer was this big thing in the center of the spaceship, and it was controlling everything. No one is imagining that you're going to carry a computer on your hip,
Right.
plus entertainment on your. This was not, because it's information,
Yeah.
and distributed information is what that is. All right, so we do send energy, but we send it in wires, and they're insulated, so you don't touch the wire and get electrocuted. That's the electricity version of a laser.
Right.
Right. Yeah. Here's the wire sending energy. Here, go grab it with two hands. No, you're not going to do that.
Now go stand in some water. Hold this. Hold this and stand in a puddle.
Okay.
I just took out some insurance on you.
Got time for a few more questions in this segment. Okay.
All right. Let's this is Zachary Sprodlin. Pretty sure I said that right, Zachary. Zachary Sprodlin wants to know this. Given your vast knowledge of physics, what are your thoughts on a holographic universe? Okay, I've never heard anybody ask this question. This is okay.
Yeah.
Do you believe the universe to be holographic in nature? If so, do you think we should be researching more about the perceived difference between the particles and waves, or are we already doing as much as our tools will allow? What are your thoughts on nature of waves versus particles and this perceived separation therein.
Okay, that's a whole other thing. But
Yeah,
let me start with the holographic universe.
Okay, cool.
I don't claim to be like a total expert in the holographic universe, but I'll share with you what I know and my understanding of it. There are calculations you can do that shows that in a black hole and the event horizon, that's the point of no return,
Okay.
that if you fall through that event horizon, all the information contained within you gets remembered at that event horizon.
Okay.
Okay? Okay. So that's a little bit spooky because you can ask the question, are we something real or are we just some
Imprint. Just an imprint
of some other thing that's
that
real?
was real. Right.
That's correct.
That's it. That's
It's almost like the Plato shadows
right.
argument or conversation that you have. Is there some higher reality of which we are just shadows representing it? And so it's a spooky idea that has sort of theoretical taproots, but I wouldn't know how to test that. Maybe the folks who came up with this have thought that through, but I'm not there with them on that. I don't know how you would test this, but usually if the theoretical underpinnings are working and they're based on other theories that are well tested, like relativity and black holes and all this, you want to take it seriously. They didn't just pull it out of the ether. Okay?
Right.
They were so that's an intriguing fact. Now, waves and particles, the duality, yeah, matter is waves and particles.
Right.
Okay. Wait, do you know why an electron microscope works?
Because it costs a lot of money. I don't know. I just know they're really expensive.
Why is the word electron in the same phrase as microscope? Microscopes use waves, light waves.
Right.
Okay. Well, you can't. Can I blow your mind?
Go ahead. Better that.
Are you seated?
I'm seated.
Okay. Here you go. Doesn't make sense that with whatever microscope you're using, you cannot see detail smaller than the wavelength of light you're using to illuminate the object.
That makes sense.
Does that make sense?
Absolutely, because
that's your blunt.
That's what you're looking at.
That's what you think.
Right.
Okay.
As a matter of fact, you couldn't see it no matter what you're looking at. If there is no light, then you don't see anything in the microscope.
Anything.
That's it. You see nothing.
So you need some light. So now you turn on the light. All right. Now, if I'm using red light, red has a certain wavelength.
Right.
Okay. But if I use light that's shorter wavelength, so orange or yellow or green or blue, of the visible spectrum, blue or violet has the shortest of the wavelengths.
Okay.
So if I have a violet light microscope, I will see detail better than I would in a red light microscope.
Right.
Okay.
You'd also see all the really nasty cruddy stuff because it's a black light and it's just like, ooh, I don't know what was on this slide.
That's if you go.
These people.
That's if you go ultraviolet.
Right.
That's if you go ultraviolet.
Right.
Not just violet.
Not just violet.
Ultraviolet. Yeah. Get your ultra going. Right. So here's the thing. It also means you can pack more information into a certain sort of size. It's why Blu-ray players have higher resolution than regular CDs.
Right.
Because regular CDs didn't use blue lasers.
And who knew streaming was going to take them both out? Regular CDs and Blu-ray.
Sorry, let me explain. CDs are what we used to,
exactly.
DVDs.
For you kids out there. It used to be something called a CD.
Used to end up at a thing. Right.
But go ahead.
Okay. So the point is, an electron has a wave associated with it that is in the realm of deep UV into X-rays. So if you illuminate a source with electrons, you basically have X-ray wavelength light telescope.
That's very cool.
That's what you have, and you can see. That's why if you see pictures taken for an electron microscope, you're seeing the fibers on the microbes.
Right. Exactly.
It's like
nasty. That's amazing.
Yes,
because you're using The wave
The wave
of the particle.
Of the particle.
The wave of the particle. Damn.
Bam.
Damn.
Bam.
Yo, that's
Bam.
hot.
Bam.
That's hot.
And so my point is, there is no meaning for you to ask, is it a wave or a particle?
Right.
It is both.
It is both.
And just because your brain can't wrap your head around it doesn't mean it's not true.
Wow.
We don't have, when I say your brain, I mean our vocabulary,
right.
our awareness of a reality requires that we choose, it is this or is it a that? Is it a book? Is it a chair? Is it are you a this or you're that?
Right.
Okay?
Right.
This is, we're forcing this in ourselves because we like compartmentalizing. This is part of the gender thing. Are you a boy or are you a girl? Right. Which is it? Okay?
Well, I haven't decided.
You haven't decided. So this forcing seems to be a deeply human thing.
Right.
But when it's time to understand the universe,
not nature.
Not
doesn't necessarily have to be nature.
It's not cosmic nature.
Oh,
yeah.
Okay.
You got it. We got to take a break.
All right.
Okay. We are in Neil deGrasse Tyson's office hours. But you can pull that query from wherever you want in the universe. We got Chuck here to mangle your name.
Yes.
As he
absolutely.
You got a little better, Chuck.
You know,
little better. I want to. I'm an educator. I want to give.
I think it's part of the charm of the show, the fact that I can't read or that I can't figure out anybody's name.
All right.
So let's move on to Kyle Ryan Toth. How easy was that?
Kyle Ryan Toth. Three syllables.
Three syllables.
You got all done.
Kyle, man, thanks, bro.
Oh, the Ryan is 2 syllables.
Yeah,
sorry.
Ryan is 2, yeah.
Mm-hmm.
Not when I say it, though. It's Ryan.
Ryan, come on down. It's time for dinner.
Hey, Ryan. Ryan. How you doing, man? Everything's what's it. How you doing, man? All right. Kyle says.
Who was it? It was Jeff Foxworthy. Who said in Texas there's certain words that are like single syllable words, but they're multiple syllables.
Yes.
Like, I don't give a shit.
Right. And it's one word, it's one syllable, but yeah. That's like I have a friend, he was like, if you're Italian, Jeep is sounds like one syllable, but it's a whole sentence. You know, so Jeep. Yeah, not yet. You know, but
I don't know what that means. Oh, Jeep. Why is that if you're Italian?
I don't know. That's what he told me. So.
Oh, you mean Italian descendants speaking like within a Brooklyn accent?
Yeah.
Hey, Jeep.
Hey, Jeep.
Oh, yeah. Okay,
right.
That's
yeah,
right.
Exactly.
I'm thinking pure Italian. I'm saying I'm not getting that.
Yeah.
Right.
No,
sorry.
No, this would be right. The
Mm-hmm.
diaspora Italian.
I got one.
Go ahead.
Know what I'm saying?
No, yeah, and wait.
Okay, that is, do you know what I am saying?
Right.
Do you know what I am saying? Know what I'm saying? Know what I'm saying?
Know what I'm saying?
Know what I'm saying?
And y'all mean?
Y'all know what I mean?
Yep.
Y'all.
There you go.
Y'all mean?
There you go. Y'all mean? All right, here we go.
Know what I'm saying?
So,
I'm to the rest of this show. I'm going to say, I'm going to give the answer. Know what I'm saying? All right.
All right, here we go.
You know what I'm saying?
Here we go.
How do you spell it? N-O-M apostrophe S-A-I-N. Know what I'm saying?
Know what I'm saying?
Know what I'm saying?
Mm-hmm.
Mm-hmm.
All right.
Mm-hmm. How do you spell mm-hmm?
Mm-hmm.
It's unspellable.
No, it's mm-hmm.
Mm-hmm.
Mm-hmm. And if you're a black woman, it's mm-hmm.
Oh, the hands got to get all in there.
Mm-hmm.
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 That's the same thing. You just went a higher octave.
Well,
That's
no,
all.
the pitch actually connotes the feeling behind it. Mm-hmm. So there's the affirmation. Mm-hmm. It's like, baby, you look good. Mm-hmm.
Okay.
And then it's just like, I didn't go to work today. I'm sorry. Mm-hmm.
Okay.
See, yeah.
So the pitch carries meaning.
Carries meaning.
Even though you're saying exactly the same thing.
Same thing, but it's all in the pitch. You know what I mean?
Okay. That's good. I learned something today.
And then there's mm-hmm.
No, that's good. That's a you are lying through your.
That's it.
That's
You're absolutely right. It's
you are lying.
Right.
Mm-hmm.
Better known as Negro, please. So there you go. Here we go. This is.
I got a word where the pronunciation changes just by capitalizing the first letter.
Wait a minute. Go ahead.
No. You'll get that later. Okay, go.
Oh, what a tease. All right. Oh, well, okay, here we go.
You want the word? I'll tell you what.
No. Let's make it a tease. We'll do it after the question.
After the break.
Question.
After the next break.
After the next break. Well, that's a real tease.
That'll keep you coming back.
You got to stay here now.
You are forced.
You are forced to be here. Okay, here we go. Imagine a planet orbiting close to a black hole and experiencing extreme time dilation. How would outgoing signals of electromagnetic communication be affected? Will we still receive such signals? Would they be distorted and or appear very slow paced?
It still goes at the speed of light.
Right.
If the planet is outside the event horizon, it's not trapped and it's in orbit. Yes, it is in a deep gravitational well.
Right.
There is very serious time dilation relative to anyone looking at them.
Right.
They will send out a signal, and the energy of their light as it comes out will it will continuously lose energy, so that by the time not speed, it'll still come out the speed of light.
Energy.
But if it starts out at a high energy band of light, by the time it gets out, it will be a very low energy band of light.
Interesting.
Yeah, so you're going to get very low energy.
See, and that's counterintuitive to what you would think, because you would think that it would lose speed, but you can't. Light can't lose speed.
Not light. That's
Light
right.
cannot lose speed.
And by the way, a way to think about this is, if I send a beam of light, there's a certain amount of energy, and I do that in 1 second, let's say.
Right.
Okay? But now I'm looking at you, and what you're calling 1 second now takes an hour for me.
Okay.
Then that amount of energy, that if it's packed into 1 second delivery time, has a certain intensity to it.
Right.
But for now, it's taken you an hour to send out that energy, as far as my watch is concerned.
Right.
So the energy gets diluted over that ascent from the black hole.
Interesting.
So, yeah, it's called a gravitational redshift.
Right. Oh,
That's
cool.
what it has a term.
Yeah.
There's probably a wiki page on it. Because I got good people.
Yeah.
My astrophysics, my community. I think we got some of the best wiki pages, accurate wiki pages out there.
And by the way, it's a hard page.
No. Comparing with other sciences, I think we do a good job.
No, you guys do a good job.
We do a good job. Gravitational
redshift. What you
redshift.
don't try to do on that wiki page is make it easy for regular people like me to understand.
Look, gravitational redshift is there.
Gravitational redshift. All right, that's a great. Hey, first of all, that was a great question, Kyle.
Yeah.
So thank you so much. All right.
What else? Bring it on.
Let's go with Annie C. Hickman, and Annie wants to know this. She says, "I am a teacher and a manual."
Give it up for the teacher.
Yeah, give it up. Boom, blow it up for the teachers. And a manual, because God, are they making such a sacrifice to just waste your life on these kids.
Damn, Chuck.
You know I'm joking. My mother was a teacher. I have nothing but the utmost respect for teachers. She says, "I am a teacher and a manual wheelchair user. From time to time, my students and I wonder if a wheelchair could be powered in space with fireworks, or perhaps they are ready to get rid of me."
To send her up
Because
there.
they want to send her to space and put fireworks on her wheelchair, since fireworks are rockets.
She's thinking about propulsion here.
She is thinking about propulsion. Also, would having mobility issues on Earth be erased in space since there is no gravity? If you float around the space station, for example, aren't you using your legs for the need to balance? And that's a great question, because people would think that in zero gravity, that your movements might do something in terms of affecting the way you drift about in zero gravity. So what is the answer there?
So first, great question. And so I presume it means she has power, she has arm power to propel her wheels. All right. So that's a key element of this. So first of all, in space, you don't need the wheelchair. You have a wheelchair so that you're not on the ground, right? So when I say in space, I'm referring to 0G in space. Right. Just take that as a given here. So if you're in space, generally people are not maneuvering themselves with their legs.
Right.
The spaceships are designed, space station is designed to have grips.
Oh, you're right.
Okay,
I've
so,
never seen them use their legs. They're always grabbing little
they're
grab
grabbing,
and then they pull themselves.
and they swim through
like
the air.
swimming.
Yeah, exactly. And so you don't want to go too fast because you have to stop somewhere at the other time, and you got to like be ready to stop.
Right.
So if you have full use of your arms and your arm muscles, you'll be doing what everybody else is doing on the space station.
Oh man, that's so cool.
So now the difference is you won't be able to do some of the sort of acrobatics that they do to show you. So for example, one of them is they'll start rotating and then they'll bring their knees up to their chest. You might be able to pull your own legs up if you don't have use of your legs. You just reach down and grab them. Right. But otherwise they're pulling their knees up and then they see that they spin faster. Right. And they're just having spinning fun. Right. Like when an ice skater brings their arms in, they spin faster. Right. If you bring your extremities in and you had a slight rotation before, you have a faster rotation. Right. And in case you don't feel nausea enough for being in 0G, now you can just spin and then you throw up right on the spot. Paint the walls.
Yeah, go ahead and paint the walls.
Yeah, if you're spinning while you throw up, then there's this spiraling.
Oh, that's a beautiful
effect.
Picture.
It's a beautiful picture. So I don't think NASA shows us.
So now back to her
she's fine in
wheelchair
space.
and the rockets. Now, so here's the thing. Because I'm thinking in my head.
It's not about the chair.
No. I'm talking about what she was saying. If you put rockets on a wheelchair, but on the wheels themselves, would you propel yourself through space in that chair, even though you don't need it, or would the rocket just spin the wheel in place?
So, what'll happen is because the wheel is on an axle, and so now you're putting something called torque onto it. Torque is a force that causes something to rotate. Okay. I've always loved the word torque.
It sounds powerful.
It's a badass word.
It is.
Yeah. You know? Yeah, give me some torque.
Exactly.
Plus, the car folks all like torque,
they love
too.
that.
They love it.
Yeah, 600 pounds of torque.
Foot-pounds.
Foot-pounds.
It needs a distance and a thing.
And a
right, because it's a distance from the point of rotation. How many feet away and how many pounds force to push it. So what you'll do primarily is rotate the wheels. But there's something called conservation of angular momentum. So if you're in space and you wanted to keep your wheelchair, if you sent wheels rotating one direction, something has to compensate and rotate backwards. Okay, so you'll push the wheels that way, and you'll just rotate in opposite.
So the two of you will be going in opposite directions, spinning around.
Correct. So what you want is, if there's a force operating on you, you want that. This is inside baseball here. You want that line of force, if you extended it, to go through your center of mass.
Right.
And that way your entire system moves.
It's just moving all at once.
All at once.
Everything's moving
If you're off the center of mass, you're going to start rotating.
You're going to rotate.
Yeah. You have some movement forward, but a lot of that's going to go into your rotation. And you want to be stable out there.
So there you go, Annie. What you want to do is lose the wheelchair.
Lose the wheelchair.
You don't need it. You don't need it.
You don't need it.
Yeah. Very cool.
And she likes fireworks rather than just those jetpacks. So you can take like Roman candles or whatever, light it. And since that has a Roman candle is an intermittent, right? So you can just adjust it.
Hold it where you want.
Where you want.
And let it pull you.
Yeah.
Very cool.
Very cool.
God, I want to go to space now. God. Yeah. Okay. And throw up all over everyone. All right, do we have time for another one?
Yeah. A couple more. Let's do it.
Okay, here we go. This is Jay deGator. Jay deGator wants to know this. We'll
go with that, Chuck.
Yeah.
Okay.
Hey, man. Hey, Jay, I'm sorry.
We'll go with that.
Yeah. So, yeah.
You know what I'm saying?
Yeah. It's deGator, you know what I mean?
No, yeah. I know what you mean. You know what I'm saying?
All right, here we go. All right. What does the merging of black holes mean for the future of the universe? Could the universe eventually, if it does start a sort of contraction phase, be the victim of a collective hypermassive black hole? Could we be left with a singularity or a black hole containing all the information in the universe waiting for the next big bang to trigger? Or does the universe have more not so distant problems to worry about?
Prioritize your
issues.
Right. So black holes are not as voracious as lore leads us to believe.
Right.
There's a black hole in the center of our galaxy.
Okay.
And it's what we call a supermassive black hole. I forgot the forgot the exact mass. Hundreds of thousands of times the mass of the sun.
Wow.
So I'd last at 600,000, but it might be a million. I forgot the number, but it's large.
Yeah.
Okay. And the formation mechanism is still a little bit of a frontier in my field. You can merge two black holes if two galaxies collide.
Right. And we've seen that happen.
It's happening all the time,
Right.
every day, all the time. And so as they collide, the black holes will ultimately find each other.
Okay.
And then they will merge. And then you have a black hole twice as big.
Right.
But the black hole's not reaching out. If you would not otherwise fallen into a black hole,
Right.
you're not going to now start falling into the black hole. We are safe.
It's not a drain.
It's not a toilet bowl drain. Right. So we're not going to one day land.
Not cosmic poop.
Right.
Well, some of us are.
Land in that. So no. In fact, in the very distant universe, black holes ultimately will evaporate, according to Hawking radiation. It's a really interesting phenomenon.
So now, okay.
Can I tell you what the phenomenon is?
Go, please.
Okay.
Yeah.
So a black hole has very strong gravity.
Okay.
Well, how much gravity does it have? Well, you can think of the gravity having a density of energy. We call it the energy density of gravity. Okay. In its vicinity. Every now and then, spontaneously, that energy becomes particles, according to E equals mc squared.
Okay.
It'll do that just spontaneously. And you make a particle pair, a matter and antimatter particle pair, and they go in opposite directions.
Oh.
Okay?
Okay.
Okay. By the way, they have to go in opposite directions so that the momentum cancels. Because it started out as just a pocket of energy sitting there doing nothing.
Right.
You can't have a particle just go in one direction and nothing canceling out that motion in the other.
Like a bazooka.
Yes, the recoil in the other
recoil
direction.
of bazooka.
Otherwise, the person becomes that's the recoil.
That's pretty funny.
That would be fun. Note to the next design.
Exactly. That is awesome.
Let me redesign that.
Why do you guys have 25 bazooka shooters? Yeah. Oh, because we got 25 shots.
Yeah, so there's a recoil of that to send it forward.
Gotcha.
So the same with the spaceships, the rockets that take off. You recoil at the back, all the exhaust. So what point was I making?
You were talking about, so the particle, as it evaporates.
Oh, yeah. So what happens is, the energy density spontaneously makes a particle pair. One particle falls into the black hole and the other escapes.
Right.
That takes mass away from the black hole.
That is
the evaporation
of the black hole.
Yes. So it's very slow, but it's real.
But this spontaneous particle, basically.
It's called Hawking radiation.
It's Hawking radiation.
That's what it's called.
So it's the dissemination of the particles that are opposites and one going away, one going in.
Yes.
And then all of a sudden, if it keeps continuing, then the black hole's gone.
It evaporates to nothing.
To nothing.
Correct.
Okay.
Yeah. So we got to take a break. When we come back, you will learn what words pronunciation changes just by capitalizing the first letter.
Yes.
Oh, yeah. Neil deGrasse Tyson's office hours, where we take questions on anything. It doesn't have to be in a category.
Yeah.
And they're coming from everywhere.
Everywhere.
Chuck is helping me out here. Chuck, keep it going.
All right, let's jump right. First you got to give the answer to the T's.
Okay, I like words a lot.
Okay. So what is this word that you can capitalize the first letter and change the meaning of the word?
Completely, yeah.
Completely.
So the word is...
I feel like I'm on NPR's word puzzle.
The word is Polish.
Polish.
Yeah.
And then you capitalize it, and it's Polish.
Yeah.
So one is what you do to shine something, and the other is
your nationality.
Is the nationality from right. Very nice.
Okay. It's weird.
It is weird.
It has nothing to do with this show.
No.
But I don't know why I
So don't start a sentence with polish.
Yes, because it has to be capitalized.
Because it has to be capitalized.
Polish your shoes.
Right.
Polish my shoes.
My shoes. You racist son of a... All right.
Yeah.
Let's go to Fyodor Popov.
Fyodor.
Fyodor?
If it's F-Y?
Yes,
yeah,
it is.
Fyodor.
It's Fyodor.
Yeah.
Okay.
And last name?
Popov.
Popov. Okay.
Okay.
Fyodor Popov.
Fyodor Popov.
Hey, Fyodor.
Hey, Fyodor. Here we go. Fyodor says this. If you had to guess, where lies the great filter? Now, first of all, what is the great filter?
I have no idea yet what he's asking in this question. So please proceed.
All right. Okay. There you go. There you go. Let's move.
No, let me hear the whole question.
That's it.
What?
If you had to guess, where lies the great filter? I don't know what the great filter is. I mean, unless it's,
the great
Brita.
filter.
If it's Brita, I'm good. Where lies the great filter?
The
in my
great
refrigerator.
filter.
Filter in my water.
The great filter. Chuck, I have no understanding of that question, so we got to go to Wikipedia.
All
Maybe from that, again, I'll be able to say something.
Say something?
Okay? All right.
All right. So in that case, what I'll do right here is go to Wiki.
So you can help me out here from Wiki.
And I'll read it to you
Go.
what they say it is.
Mm-hmm.
The great filter, in the context of the Fermi paradox, is whatever prevents dead matter from undergoing abiogenesis in time to expanding lasting life as measured by the Kardashev scale.
Okay. All right. I can say something about this.
All right.
I just didn't know it was called
the great
filter.
All right.
Okay.
All
so
now all I got from that was Fermi paradox.
Okay.
I know what that is.
Yeah, so the Fermi paradox was a question posed by the great physicist Enrico Fermi,
right,
who, born in Italy, came to the United States,
nice.
Basically Manhattan Project. So Enrico Fermi posed the question, because you can run the math. You can say, all right, how long has Earth been here? How long did it take life to form? How long did it take what we call intelligence to form? Now that we're intelligent, how long does it take to travel to another planet? Let's say we have a spaceship. All right, is it a generational ship? Fine. So it takes 10 generations to get there. Then you become pilgrims. Set up tent. Now from there, you go to 2 other planets.
Okay.
From each of those 2 planets, they go to 4 more. From 1 to 2 to 4 to 8. So it grows exponentially. You can populate the entire galaxy with intelligence in a shorter time than evolutionary timescales. Okay, you can do it in like 1 million years or so.
Right.
Okay?
Yes.
And that's on an evolutionary... the dinosaurs went extinct 65 million years ago.
Exactly.
So
that's a very short time.
Very short.
And
it's small compared with the lifetime of a planet.
Exactly.
So, and especially the future of the universe.
Right.
So if that's the case, why hasn't it happened yet? And where are the visitors trying to populate this planet that we're on? So it's the Fermi paradox. Where are they?
Maybe they were already here.
Maybe we are.
And maybe we are them.
Okay.
You know.
So there's some religions that are based on that God is actually the aliens. Yeah.
Okay.
Yeah,
that's right on.
Okay. All right.
Hey, listen,
so
I don't judge.
Just by the fact that you said that, I don't judge how crazy people are. That's what you said. That was implicit in your.
Oh man.
So
okay.
Wait. So this dead matter. What they don't mean dead matter because that implies it was once alive. They mean inanimate matter.
Okay.
Inanimate matter evolving to become self-replicating life.
Okay.
So the question is, maybe that takes so long that it puts a damper on this whole...
On the other process.
On all the other processes.
Right.
However, that happened really fast on Earth.
Okay.
We went from inanimate molecules to self-replicating life within a couple of 100 million years.
Wow.
And once you have life was there for billions of years.
Right.
So that's not really that long.
No, it isn't.
Right. So the filter, I don't see that as the big filter. You know what I think the filter is?
What?
Whatever urge you have to colonize planets.
Okay.
And then all your descendants have that same urge.
Right.
There's going to be a point where there's a planet I want to colonize. Oh, but you want to colonize that same planet. So then what do?
You're gonna have a blood feud.
You're
with
going to
your
blood
own
feud
family.
with your own family.
Right.
Correct. And so it could be that the urge to want to expand is self-limiting because you will fight wars.
You cancel yourself out.
You cancel yourself
The
out.
very urge that causes you to strike out and discover is the same urge that destroys you in the end.
Correct.
Wow.
Right. And there are whole categories of these kinds of problems in life. For example, I don't know if this still happens if you lose a quarter between the base and the back of the seat in your car.
Right.
And you reach for it.
Right.
The act of reaching for it separates the two cushions more, and then it falls further in.
See, I'm cheap. That whole seat's coming out. Okay? I'm going to be honest.
Get in that corner.
I have actually pulled a seat out to get to money that's falling.
We got 1 minute left. Let's do lightning round. Go.
All right, here we go. You know what? This is an education question, so let's do it.
Do it.
This is
Lightning round.
Stephen Donham. He says, hey, Neil, love your show. Listen all the time. My question is about Common Core math being taught in school. It seems like a waste of time, and kids have to go through all of these extra steps to get the right answer when there were simpler ways to get the right answer when it comes to life and death and space. Wouldn't it not be better to get the right answer the fastest possible way?
Oh, good question.
Very good question.
I am not doing a lightning round on that question.
Okay.
It's too important.
It is a very
I'm
important.
going to end with my answer to that question.
Okay, so this is the end of the show, and that's why
I'm doing deep dive on educational philosophies.
Well, that's why I picked the question.
In my recent months and years.
Well, you're an education. You're an educator.
A deep dive, and I'm looking at what people have said, what have worked, what hasn't, best practice, and I have come to conclude with regard to that question.
Okay.
That what matters more than the right answer is the right question.
Interesting.
And taking a cue from Isaac Asimov in an essay he once wrote called The Relativity of Wrong.
The relativity of wrong.
Yes. Okay, so here you go. You're in elementary school.
Uh-huh.
And I have a spelling bee.
Mm-hmm.
And I ask you to spell cat. And you spell it K-A-T.
Mm-hmm.
It's marked wrong.
Right.
You don't get any credit for that because the correct answer is C-A-T.
Right.
But suppose instead you had spelled it X-Q-W. It's still marked wrong.
And that's so much farther away than
It's
K-A-T.
so much farther away than
Right.
K-A-T. In fact, you could argue that K-A-T is a better spelling than C-A-T. You know why? Because if you look up cat in the dictionary, C-A-T, the phonetic spelling is K-A-T. Okay?
That's awesome.
But you got it marked wrong.
Right.
So this urge to get the right answer.
Mm-hmm.
Yes, I don't want to diminish the importance of right answers. That has value, but it has less value than you think it does. Because in exploration, you have no answers. You're on the precipice of the boundary between what is known and what is unknown, and you're taking a step into that unknown. And you don't know what's there. You don't even know what question to ask.
I know what's there.
But,
a cat.
But you're probing, you're poking. You're trying to figure out what question to ask. And most questions don't even have
an answer.
unambiguous answers.
Right, exactly.
Can I give you an example?
Go ahead.
Okay. What's the diameter of the sun? Ask me that.
What is the diameter of the sun?
You look it up, it'll say 864,000 miles.
Okay.
Okay, fine. But in what wavelength of light did you make that measurement?
Okay.
Other wavelengths of light emerge from deeper in the star.
Right.
Okay? That's it. And if you're using X-rays, it's bigger. The corona emits X-rays.
We found that out earlier in the show because of the different wavelengths.
That's a different wavelength. So you have to specify. How high up does the atmosphere go? Earth's atmosphere. Because, well, 62 miles, 100 kilometers. We've just agreed because that's a round number in kilometers. There's still air molecules above 62 miles. That's why we have to boost the Hubble telescope every now and then because air molecules are knocking it out of orbit. Okay? So there is no demarcation line. It fades until it blends with the interplanetary medium. So we like tidy answers, but most of science is not even about the answer. It's about the general understanding of what's going on, and then you take it from there. So no, Common Core math is a good thing. It's got you thinking in ways that It will enable you to tackle a problem in the future that you have never seen before. Right. And if you're in space, it's not about knowing the right answer to a pre-designated question. It's about figuring out an answer to a question no one has asked before.
Right, right.
And so you need the tools and the methods and the power of inquiry to accomplish that.
Wow. There you go. Drop the mic. That's a very good answer.
I'm saying.
I like it.
I'm writing this up.
It makes sense.
It's going in the next thing.
All right.
Chuck.
This was good, man.
Always good to have you.
Yeah.
Dude. You know what I'm saying?
You know what I mean?
You know what I'm saying? This has been Star Talk. We're recording this in my office.
At the Cosmic Crib.
At the Cosmic Crib at the Hayden Planetarium in New York City.